all self-report their weights accurately. Listed in the accompanying table are 35 self-reported and doctor-measured weights in pounds of 35 randomly selected adult female subjects. So you can look over here in the table and you can see this. The first sample is the reported weights, and it consists of all the numbers in this column right here. So that is like sample 1. And the second sample corresponds to measured weights, and all the weights you see here, this is basically our sample 2. And there are 35 of each. It's important to notice we are told that each row corresponds to the same woman. So her reported weight was 110 pounds, and then when she was measured by the doctor, it was actually 109.6. For the second woman in the table, her reported weight, which goes into the first sample, is 132, but then when it was measured, it was 132.9, and that went into the second sample, the doctor measured sample. Okay, so our goal is to use a 500th significance level to test the claim that for adult females, the self-reported weights tend to be less than the doctor-measured weights. So this is the claim that we want to test, so I just want to highlight that. So self-reported is less than doctor-measured weights. Assume that mu sub d is the mean of all differences d for the population of all pairs of data. So that is for all adult females, not just the sample. Where the difference d is defined as self-reported weight minus doctor-measured weight. Okay, so that's also important to note that d here represents self-reported minus doctor-measured. Okay, so if self-reported tend to be less, then we expect self-reported minus doctor to be negative. I just want to be a little more clear about what D represents in case you forgot from after reading the book. Okay, so D is what we call the difference. And we are told it's self-reported minus doctor measured. So in this case, it would be for the first woman, it would be just the difference between what she reported and what was measured. And you can see for the second woman, it would actually be negative. For the third woman, it would be negative 10.6. For this woman, it would be negative 0.3 of a pound. So that's what the difference D represents. It's just for each pair, we just calculate the difference and we make sure the order is correct. And we're going to get a whole list of differences. Before we move on, a couple other things I want to point out are that the 35 women in this study we are told that they are randomly selected. We're also told that there's 35 women, so that's a larger sample. It's more than 30, so we know the central limit theorem will kick in. We also know that the data, each row comes from the same woman, so our samples are paired. So I just want to add that. And the samples are actually what we have is 2 dependent samples. So the first step in the hypothesis test is we want to state the null and alternative hypotheses. Since we are working with matched pairs, or in other words, dependent samples, our null hypothesis is always going to be the same. It will always be H naught is that mu sub d is equal to 0. So this means that if I were to take all those differences d for the whole population of all adult females, the mean would be 0. In order to determine the alternative hypothesis, I'm just going to take another look at the claim. So remember the claim was that for adult females, the self-reported weights tend to be less than the doctor-measured weights. Okay, so this is, and remember that the difference D was self-reported minus measured. So if self-reported is less than measured, and so the correct alternative hypothesis is that mu sub D is less than 0. The second step for the hypothesis test is we want to check the requirements and calculate the test statistic. Gathering the sample and summarizing the data has already been done for us. If you recall from carefully reading the example, we know that we are working with a random sample of 35 adult females. The sample size is large, it is greater than 30. This means that we can use the technology and the formulas for this section because the central limit theorem tells us that the distribution of sample means is approximately normal. We also know we're working with dependent samples. Each reported weight in sample 1 corresponds to a measured weight in sample 2, and they are matched because they belong to the same woman. We do not assume anything about the population standard deviations. We do not assume they are known or that they are equal. Our next step is to calculate the test statistic. And whenever we're dealing with matched pairs or dependent samples, these two samples, we will be using technology most of the time. So I am just going to copy and paste my data into StatCrunch. And if you have a spreadsheet, you can also upload that to StatCrunch using the data command. So here I am in StatCrunch, and I'm just going to paste my data. Okay, I'm careful that reported and measured ends up in the top row and not as, the first line of data. So there you can see I have 35 data values. So the correct command is stat, tstats, and then we're going to go down all the way down to paired data. Sample 1, remember, D was equal to reported minus measured, so I'm going to be using reported for sample 1. For sample 2, we're going to be using measured. And if reported minus measured is my difference, remember that my alternative hypothesis will be less than. And I just click compute. Here's the readout. The first thing we note from the StatCrunch readout is it calculated the mean of all the differences. So we find that the -3 here is the sample mean of all the differences. So on average, women underreported their weight by about 3 pounds, okay, in the sample of 35. The test statistic was approximately -1.67. And the p-value was 52 thousandths. So we calculated the test statistic to be about t equal -1.67. Let's take a second to interpret that. This means that assuming the H naught is true, so the null hypothesis is true and the mean of all those differences is just 0, so there's no, underreporting going on or overreporting. The mean of the sample differences reported minus measured, which is about -3 pounds, is about 1.67 standard deviations below the null value, which is 0 pounds. In other words, the difference between what the sample estimates the population mean to be, which is about -3 pounds, and what the null hypothesis claims that the mean of the differences to be, which is 0 pounds, is about 1.67 standard deviations. Recall that step 3 is where we calculate the p-value. According to StatCrunch readout, the p-value we got was 0.052. Let's interpret the p-value. A p-value that is 52 thousandths means the probability is 52 thousandths, which is pretty borderline of observing data like those observed if the mean of the differences is really 0. In other words, if the null hypothesis is true, that means that mu sub d is 0, then there is a 5.2% chance of getting a sample of size 35 having a mean difference of, and let me just change that, 3 pounds, about, -3.05 pounds. More specifically, if the null hypothesis were to be true, then there is a 5.2% chance of getting a sample of differences of size 35 having a mean difference as small as -3.05 or smaller. In step 4 of the hypothesis test, we just state our final conclusion. Remember that we're using a significance level of alpha equal to 5/100. We found the p-value to be equal to 52,000, which is just slightly larger than our significance level alpha. When that happens, we do not reject the null hypothesis, but it is very close. The data conclusion is that the data do not provide sufficient evidence to conclude that for adult women, reported weights tend to be less than measured weights.